This
Hey,
conference will now
uh,
be recorded.
so what is cooking? What is on the menu for our conversation today? First, we're going to start with just a KBS market overview. What are we seeing in the market? So like I said, I cover across the entire country. So we've seen a lot of different pockets and different changes happening specifically within the kitchen ventilation market. I know when I was brought on to talk today, one of the topics that we wanted to hit on was cooling in kitchens. So we'll certainly talk about that and what we're seeing across the country. But we're going to go through a KBS market, just overview, components overview. There's no way of talking about kitchen ventilation systems without talking about the components of that given system. So we'll talk on a high level on what those components are. Next, we're going to go into the design considerations in kitchens. Kitchens are really pretty straightforward to design because code and IMC is going to very much structure what your airflow capacities are and what your design considerations are going to be. But we're going to talk about what those are and then potential problems to mitigate in kitchen designs. Next, we're going to go into evolution of kitchen design, and that's going to be kind of the past of kitchen design, the present, and a little mixture of the present slash the future. So what that all comes into play is, hey, the age-old question in the kitchen: do we heat this air? Do we cool this air? Do we dehumidify this air? How does a standard dedicated makeup air system, regardless of manufacturer, fit into that system? And then now we're seeing more DOAS units or dedicated outdoor air systems coming into kitchens that are going to allow for dehumidification. So what are we seeing across the country? Why is that coming in from a design standpoint? And we're going to look at three different potential designs of a space and talk about the advantages to how it's designed, disadvantages, and well, I guess the third option. So finally, we're going to wrap up with grease filtration, specifically around pollution control units, as those have become a much hotter topic across the country. So with that said, we're going to jump into the KBS market overview and components. So we can't start talking about the KBS market without understanding, or the kitchen ventilation system without understanding the market that it operates in. First and foremost, kitchen ventilation, whether it's the exhaust fans, makeup air fans, the exhaust hood, the grease duct, it's all a system. So a kitchen ventilation system has historically been in the market where above ceiling mechanical contractors and design folks are getting involved with your above ceiling applications, so your grease duct, your exhaust fans, and your makeup air fans. And then below ceiling is tending to be a food service equipment dealer, food service consultant, someone who specializes in the actual below ceiling side of the thing. So what that means is that across the country, we have kind of a split market in one system. And ultimately, the biggest issue that we see nationwide is when this gets to site is wait, who designs what? And ultimately, we're coming in and we're seeing a lot of one system, two entities. So who is accountable when something goes wrong? One of the most commonly missed items in the scope of a kitchen ventilation design is the controls, because the above ceiling contractor or designer thinks that's part of the below ceiling and vice versa. And then the controls that are required per code are not specified in that scope. What we're seeing, again, these are nationwide numbers, but what I've been seeing is that about 70% of the market is being either sold or designed through the food service equipment or the food service consultant wing of the market provided by owner type. And then about 30% is being sold through the mechanical contractor. So let me correct when I say that. About 70% of the market is moving through the food service equipment dealer, whether that be the food service having all of the fans and the hoods, and about 30% is moving through the mechanical market. So it's a very segmented market. The trend that we're seeing nationwide is that more and more of either the purchasing or the design or the overall responsibility for the kitchen ventilation system is shifting more into the mechanical side of the market, because that's where more of the mechanical engineers are and the HVAC experts are. So I would anticipate that the market is going to move more towards the mechanical market as we move forward. But again, that's different pockets in the country. So here in Minnesota, I can speak to what I see here in Minnesota. It feels like it's more of a 60-40 split between food service and mechanical. And then, in other areas of the country, it's more of an 80-20 or a 50-50 split. It really does vary by region who is responsible for each one of these components in this system. So regardless of who's responsible, in order for a kitchen ventilation system to work, it needs to have all of the proper components within it. So the components of that KVS system would be your hoods, your fire suppression, your exhaust fans, makeup air, controls, and then finally grease duct, again, all being tied together and all working in unison. So we're going to go through the different parts of these the parts of these components. For a lot of y'all, this is going to be a review of stuff that's been in the industry for a very long time. These components are not going anywhere. But once we get through that, we'll jump into some more of the design considerations. So first and foremost, the first part of this kitchen ventilation system, pretty basic, but it's the hood. So hoods in the market, you're going to have either a type 1 grease producing hood that are listed to UL 710 listing standards, or you're going to have a type 2 hood for a non-grease producing application, for a heat only application, or for when we have for when we have a condensate or a dishwasher fan in here. It's pretty straightforward, and again, code's going to dictate a lot of what type of system you're going to go to. Is there grease being produced in this system? Then, hey, it's a type 1 system that's going to require all of the components that we're going to talk about. UL 762 rated fan, fully welded grease duct, fire suppression system, everything that we'll go through here. Is it only condensate or is it heat? Well, then it's a type 2 situation, which is going to be a lower airflow rate, and and your fans are going to be rated to a UL 705 listing. Now, the most common question that I get, because again, this is pretty straightforward, type 1 versus type 2, but the most common question that I get as a part of my daily job in speaking with engineers is, hey, Mike, I have a convection oven or a combi oven that is going into a school or it's going into a bakery. Do I really need a type 1 system, or can I utilize a type 2 heat only system? And again, it's going to depend on the amount of grease that's being produced. And if there is in my experience, it's always going to be the local code the local authority having jurisdiction is going to be the one that's going to ultimately dictate what type of system that we utilize. And in my personal experience, most code officials are going to go to the worst case scenario. So, hey, is there a probability or a possibility that at some time in the future, this convection oven or this combi oven that is currently being used for heat only, is there a possibility somebody could throw a pan of grease or a pan of bacon in there and make quite a bit of grease production? If yes, then most folks that I've interacted with are going to go on the more conservative side and require a type 1 system. But that's really the only time you really have to think about, is this a type 1 or a type 2 system? It's these kind of in-between items where they're truly going to be is it truly just heat up, reheat, that's not going to have any grease production, or is there a possibility for grease production? So not a lot for you all to think about on that side of things, but those are your two options for your hoods. Next, we're going to jump into the different exhaust hood configurations that we have. So first and foremost, the standard wall canopy exhaust hood is going to be your standard configuration. So this will be a canopy hood, typically 24 inches or 30 inches tall, mounted along a wall with baffle filters, with some sort of grease filtration, lighting, and again, a 24 or 30 inch top. Now, the next configuration is going to be a wall canopy hood, but a tapered front. So these hoods are required per ADA, are required to be hung 80 inches above the finished floor. But if you're doing a renovation or if you have a lower ceiling application, there may not be a scenario where you can hang this hood 80 inches above the finished floor and then have a 24-inch box on that hood. You may need a lower ceiling requirement. And in that case, you're going to be looking for a tapered styled hood. Tapered styled hoods are going to typically come in anywhere from 18-inch fronts down to around 12-inch fronts. And again, the reason for that hood is you're still going to hang that at 80 inches above the finished floor as required by ADA, but it's going to lower your overall height of your exhaust hood system. The next common configuration in the market is a double island back-to-back hood. So this is going to be a scenario where you have appliances running down, they're back-to-back to each other. So you're going to have probably about 104 inches of overall depth to these hoods. Now, you wouldn't manufacture a hood at 140 inches deep. You would have rigidity issues. So what you're going to do is what you'll see is a double island back-to-back wall canopy hoods. This is actually two wall canopy hoods, non-integral to each other, hung on their own unistrut, but hung back-to-back to each other so that you have the proper overhangs. Again, these are also going to be hung 80 inches above the finished floor. And one thing again, it's very basic, but one thing that I should mention is that code is going to require an overhang to the appliances for these hoods of a minimum of 6 inches from the edge of the appliance. So you're going to take your entire appliance lineup, the total length of your hood, your fryers and your griddles and whatever you're protecting. And then you're going to add a minimum of 6 inches to both sides of that hood, or a minimum overhang of 6 inches to the front of that hood. And we'll go into some different design considerations on that later. So I mentioned 6 inches for those hoods. The other hood in the market is, you'll see what's called a low proximity. Every manufacturer is going to refer to them a little bit differently. You'll commonly hear these in the industry called Five Guys hoods, because Five Guys restaurant chains were the ones that really brought them into existence. But these low proximity hoods, they're really good for fast food type establishments that are going to be utilizing fryer banks and griddles, but not very hot pieces of equipment. The reason for that is these hoods are going to typically hang anywhere from 24 inches to 36 inches above the cooking surface. So not the 80 inches above the finished floor. They're going to be right above the cooking surface. And they're typically going to have some sort of an underhang requirement of anywhere from 6 to 18 inches, depending on the application. And since they sit so low and they have an underhang requirement, they don't have to hang in that 80 inches, like I mentioned. And then you're going to have a reduction in CFM in utilizing these hoods. Thing to keep in mind is, as soon as you have ovens, or if you have really hot appliances underneath these hoods, so like you couldn't, for example, in most instances, you couldn't have a gas-fired charbroiler under a low proximity hood, because the heat of that charbroiler would be sitting too close to the fusible links in the fire suppression system and would cause the fire suppression system to go off. The final hood configuration that you're going to see in the market is a Type 2 style hood. So whether that's a heat-only hood or some combination of condensate baffles in a Type 2 hood, this is going to be the configuration of your Type 2 hoods. The condensate baffles, again, that would be used over a condensate application, such as a dishwasher, and that's going to be used to knock the condensate out of the air. Typically, you're going to have some sort of a perimeter gutter with these as well. That's going to go down to the drain line. So these are the hoods that we're seeing in predominantly used in the market. When I get to this part of the presentation, I'll inevitably have somebody thinking, "Hey, Mike, you're missing a hood configuration," and that hood configuration is your traditional island canopy hood, which are definitely still out there in the marketplace. But due to cost, what we have been seeing more and more across the industry, and the hoods have been proven to work, is wall canopy hoods in island applications. So what that would be is that first wall canopy hood with a finished back hung over, say, an appliance in an island application. And then what I've typically seen is that the capacity or the CFM of those hoods is typically increased by about 20% to account for the added space around the hood and the added potential that people are walking around this hood and negatively affecting capture. One common item missed when designing this type of hood with a wall canopy and island configuration is keep in mind that you don't have a wall at the back of this hood anymore. So you need to have a minimum of 6-inch overhang from the back of the appliances as well. That's one commonly missed item. Moving on to the next component of a Type 1 system, and that's the fire suppression system. There's two types of fire suppressions out there in the market. There's a number of different manufacturers that are doing fire suppression, but ultimately you're going to have either appliance-specific coverage or you're going to have full flood or overlapping coverage. So appliance-specific coverage is going to be far and away the most common coverage in the market. If you really think about it, these restaurateurs or universities, whoever is opening that restaurant, unless they're some large cooking operation that's changing appliances all the time, they're almost always going to keep at least the same appliance type under their hood system for the life of that particular project. So appliance specific is going to be a much more cost competitive price for that owner to open his business, because there's less material, there's less size of tanks. It's just a cheaper option that will still meet all UL qualifications. The other type of fire system that you're going to see in the market is a full flood or an overlapping coverage system. These systems, in a lot of instances, will also have a water-based component to them. So they'll have some sort of effluent dump, and then they'll have a continuous water supply coming on in order to douse the fire. These full flood systems are commonly used in test kitchens where you're going to be changing out a lot of different appliances. So some major manufacturers or major retail chains that are going to have their own brand of food are going to have test kitchens associated with them, so they can test the nutrients of their food. They can test the different how to cook these foods in different appliances. So those types of operations are commonly taking their appliances and switching them out because they're truly switching appliances because they're switching what they're testing. So that's where a full flood system is going to come into effect. The other time you're going to see it is where it's required by local code. So I can't speak to too many areas in the country that are required to have overlapping systems. Besides, I'm out of Minneapolis, Minnesota. South of us in Bloomington, Minnesota, we have the Mall of America. And the Mall of America, as a building organization, has made, they worked with the city of Bloomington in order to get these full flood systems to be required per code. The idea being that they didn't want the type 1 systems to have any variance to them. So they just said, hey, if you're coming in here, it's going to be a full flood system. But not very common that it's required by code in particular municipalities. Moving on to the next part of the kitchen ventilation system, it's a UL. So when we're talking grease exhaust, we're talking a UL 762 exhaust fan. So that UL 762 is the rating of the motor. It's removing the motor from the airstream, from the grease exhaust airstream. And then from there, it's just whatever configuration you're going to utilize. So sidewall termination exhaust fans are an option. Sidewall fans can be a little bit of a trickier proposition. You need to make sure that you're at least 10 feet away from any adjacent property lines, at least 10 feet above grade. And then most municipalities will not allow sidewall configurations over, say, solid fuel appliances. Typically can't have a sidewall termination. That's actually IMC, not local code authorities. But the other local things to look out for is over any walkways, over any operable windows or doors, anywhere where this grease could come out of the system and negatively affect the area around it, they're typically not going to be allowed. The most commonly seen exhaust fan in a kitchen ventilation system would be your upblast exhaust fan. So things to keep in mind when designing an upblast exhaust fan. The wind band of this, so they always need to have a hinged curb cap. Reason for this is a guy has to be able to lift up that curb cap and go from the top and clean the grease duct from the top of the roof. Then the wind band, so obviously this curb cap is shown to be tilted up, but the wind band of the upblast exhaust fan has to be at least 40 inches above the finished roof deck. One commonly missed item in specification of upblast grease exhaust fans is that people don't take into account the insulation thickness on the roof. So they may say, oh, this is a 40-inch tall curb or a 24-inch tall curb with a 16-inch wind band to get me to 40 inches. But they'll forget that, hey, that roof deck has 2, 3, 4, 5 inches of insulation in there. So now this wind band is not 40 inches above that finished roof deck. Utility set fans are another option when it comes to UL 762 fans. This particular utility set fan, this rendering is actually for a 705, a UL 705 fan. So if you remember, that's for a dishwasher or a heat-only hood. All UL 762 fans need to be of an upblast configuration so that you're not dumping grease back onto your roof deck or straight across as this utility set fan would be. The final type of exhaust fan that we're going to see in a standard kitchen ventilation system would be an inline exhaust fan with that motor removed from the airstream for UL 762. We're going to touch on in the last part of this presentation, we're going to touch on pollution control units as well, which is another type of exhaust fan, but it's not really your traditional UL 762 exhaust fan. It actually has a different rating to it. Next component to a kitchen ventilation system is our makeup air unit. So I'm going to touch on a couple of different types of makeup air unit, again, regardless of manufacturer. And then when we get into the portion where we're actually discussing a little bit of design, we'll talk about what we're seeing across the country when it comes to DX cooling or split DX cooling, DOAS units, dedicated outdoor air systems, or are we just seeing very common in the kitchen market is you're going to have just a direct fired makeup air fan with no cooling on it. And we'll talk about why that is. I can speak from personal experience. I was a chef at an Applebee's in Wisconsin where I went to college. Did not like cooking there in the summer. Kitchens are inherently humid. They are inherently hot. That is changing, but it's definitely a cost-based side of the business. The final component that we're going to speak on here, as far as the kitchen ventilation system is concerned, is your controls. So there's two types of controls in the market. first and foremost, controls are required per IMC to be an interlock to the exhaust fans and the makeup air fans. And the way that interlock is achieved is that the exhaust hood is going to come with a temp probe, either in the exhaust hood cavity or in the exhaust hood ductwork. And that temp probe is going to be sensing the temperature underneath the exhaust, underneath that exhaust hood. So basically, what is that doing? It's sensing the temperature under the hood. So if you turn all your appliances on, that's going to generate heat. That heat generation is going to bring you above your ambient temperature, and that's going to signal to the exhaust fans per the temperature interlock that, hey, we now need to start these appliances. We need to start the exhaust fans and interlock the exhaust fan with the makeup air fan, regardless of if the chef has turned the fan switch on or off. If it's sensing temperature, it's going to start that fan. And now I mentioned that there's two different controls types in the market. There's a constant volume control type, and then there's a variable volume control type. Constant volume is exactly what it sounds like. Constant volume is, hey, we're going to hit our minimum temperature set point, which in most instances is somewhere around 90 degrees Fahrenheit. Once we've hit that minimum temperature set point, we're just going to run these fans at 100% of design, regardless of the cooking application that's happening underneath that hood. Variable volume systems are going to do exactly what they sound like. So they are going to vary the volume of the system, typically based on some sort of temperature basis or a combination of temperature and optic sensing. And what this is going to do is it's going to vary the speed of the fans as cooking operations go up and down. So if you think about a traditional restaurant, you're going to have your prep time in the morning. So you're going to come in, the chef's going to come in at, 10 a.m., and they're going to start the appliances, and then they're going to go in back, and they're going to start chopping up the onions and doing all that prep work. Well, the appliances are running, so the fans are going to need to be running at some sort of a minimum speed, but they don't need to be running at 100% of design. And then as the lunch rush comes up, as the dinner rush comes up, that chef's throwing a bunch of burgers and steaks and running around, and all of his appliances are on. Well, now that temperature is going to increase to somewhere in that 120 to 130 degree area. In between that 90 and 130, what these systems will do is they're utilizing VFDs or ECM motors, is they'll proportionally track the temperature underneath the hood so that the fans will speed at a proportional speed to the temperature under the hood. So this isn't going to be an exact number, but let's just say that our minimum was 90 degrees, and now we're in a lunch rush, and our temperature is being sensed at about 105 degrees. So it's not all the way up to the max, but it's definitely above just a base level, stalled out cooking operation. So maybe that fan is now going to run somewhere around 75 to 80% speed, and that's all determined by the typically via VFDs and the signal being sent to those VFDs from the temp probe. The final thing that I would mention here is twofold of what we're seeing in the market and some design considerations. Prices between the two different types of units across the board have really come together. And historically, if you were going to do, like, say, an elementary school or a middle school, you would say, okay, well, I know that I'm not doing a ton of cooking under there. It's still a type 1 system, and I'm not doing a ton of cooking. So what an engineer or someone would do is they would design this with a constant volume system. Let's just say 3,000 CFM, assuming full load is 100% of 3,000. The idea being it was a lower upfront cost, so we're going to do a constant volume design. What I've been seeing across the industry over the last number of years is that even in those instances that are actually lower level cooking operations, people are utilizing variable volume systems. You also hear referred to the market as demand controlled ventilation systems, one and the same, just depending on who you're utilizing. And the reason that they'll use a variable volume system in, say, like a school application is that school is never going to get to that max threshold of that temperature. That school is going to operate typically somewhere between 50% and 75% of design. So if you're thinking about that from an energy consumption standpoint, then the long-term energy savings of utilizing a variable volume system is typically going to be a good payback. Now, is that a universal? That is what we're seeing. It's a hard and fast rule, and that just is what it is? No, certainly, absolutely not. It's kitchen ventilation design. There are no hard and fast rules for the most part, but that is just the trend that I've been noticing across the country. as these systems have become more prevalent in the market. The final thing that the kitchen ventilation system, the final interlock that it's going to do is that these systems, when you have a dedicated makeup air system, a makeup air unit, these systems, like I said, they're interlocked. The exhaust fan and the makeup air fan are interlocked to operate in conjunction when they're sensing heat. However, if there's a fire situation, so if the fusible link in a fire suppression system melts and it dumps the fire suppression system, or if somebody pulls the manual pull station on that fire suppression system, the exhaust fan per code is required to go up to 100% of design, and the makeup air fan is required to turn off so that you're not feeding fresh air into that fire. That is important to remember for the variable volume system. So even if this thing is operating at 50%, if somebody goes and pulls that manual pull station, code requires that that fan operate at 100% of design. And again, these control packages are going to have all of that interlocked within them. So now that we have a base understanding of what goes into a kitchen ventilation system, and I know for a lot of you that was extreme review and you're saying, hey, Mike, I know this. Hopefully it's good information for other folks. But now that we understand the basis of what goes into a kitchen ventilation system, how do we design these systems? So I said to start that in my opinion, designing kitchen ventilation systems is relatively easy. And the reason for that is that code is going to dictate a lot of what your CFM or what your capacities are going to be. And then from there, there's only a couple of design considerations to think about mitigating or problems that can come up with your design. The biggest question in design considerations is going to have to do with your makeup air. It's going to have to do with the fact, hey, am I going to utilize a heat-only makeup air, a heated and cooled makeup air, or a full DOAS unit with heat, cool, dehumidification, and the different price points of not only your initial product, but also your ongoing energy consumption we'll come into, and we'll get into that. But exhaust airflow rates. So this is going to be largely dictated by IMC from the base standpoint. IMC section 507 is going to dictate your hood construction and your capacity of those hoods. First thing to note is kind of an update to IMC is that IMC no longer classifies these hoods based on temperature. They used to classify these hoods based on temperature. They've now made it a little bit easier. These hoods are classified just based on a duty rate. So based on light for type 2, medium or heavy, and then extra heavy being for a solid fuel application. Now, I'm not going to talk too much about solid fuel in this presentation. If there's follow-up, I can certainly have those conversations, but it's just important to note, if you have a solid fuel appliance, that appliance needs to be on its own exhaust hood system with its own exhaust hood, its own exhaust duct, and its own exhaust UL 762 exhaust fan. So it's extra heavy, has to be on its own application or its own system. Now, the other types, so your standard appliances would be heavy or medium. So what determines if this is going to be heavy or medium? It's going to be the worst case scenario of the cooking appliances underneath the hood. So let's say our appliance lineup is one oven, one griddle, one fryer, and a gas charbroiler. That gas charbroiler, that's going to be my heavy application. So now I have to design this entire hood under a heavy classification. So what does that mean? That heavy classification is going to be designated by IMC for CFM. So hoods, and again, review for a lot of folks, but got to cover it. But hoods are going to be specified based on linear, they're going to be designed based on linear feet of hood. So we're going to come down here. We're going to see that the IMC airflow minimum rates for a heavy duty hood is 400 CFM per foot. Now, IMC section 507 states that if the hood manufacturer is UL 710 listed, then that manufacturer's UL listing supersedes IMC minimum. So you're going to have a UL 710 airflow minimum. This is going to vary by manufacturer, but what I always keep in mind when I'm talking about UL 710 minimums is that these are perfect lab conditions that they were testing these in. So I would never recommend designing a system at a UL 710 minimum airflow. I would try to find somewhere in between based on based on kind of your history and your recommendations. So if you asked me, Mike Jervanak, where would I design a medium or a heavy duty hood? Now, I wouldn't design it at a UL 710 minimum because that's way too small. But I also wouldn't design it at an IMC 400 CFM per foot because the hood is going to be UL 710 listed. So I would recommend sizing this at about 275 feet per foot, CFM per foot, excuse me. And you're going to get a different answer on CFM per foot depending on what individual you talk to, whether that be in the engineering community or in the manufacturing community. It really is just based on experience and based on the specific appliance lineup. So let's say I had a gas charbroiler, but it was only 2 feet wide, and it was in the middle of my appliance lineup, and this wasn't a very heavy duty restaurant. It was maybe more of they have the charbroiler for one thing, they just don't use it a lot, right? I may at that point take that into consideration and say, well, let's save some energy. Let's go 250 CFM per foot, or even down to 240 CFM per foot, just so long as you don't go under the UL 710 airflow minimum. And again, I would almost never go to that for any one of these. So we now have our capacity of our CFM. In most instances, your supply CFM is going to be correlated to your exhaust CFM. So if you're using a dedicated makeup air system, best practice is to have 80% of your supplied air be supplied by your dedicated, 80% of your exhaust air be supply air from your dedicated makeup air system. So now I know, and then the rest of that 20% would be accomplished through transfer air, keeping a kitchen in a slightly negative standpoint. So now that I know my design CFM, I know that I'm going to have, let's say, a 10-foot hood. It's going to be 275 CFM per foot, so it's going to be 2,750 CFM, and 80% of that is going to be supply. It's going to be what my supply is going to be. The only other design consideration I have to keep in mind is the velocity in my grease duct. So nationally, and it's different in some pockets, but for the vast majority, nationally, IMC has moved to a minimum velocity in grease duct of 500 feet per foot. Traditionally, it had been 1,500 feet per foot, but it's mostly now down to 500. The reason that it went from 15, and I personally would recommend designing at 1,500 feet per minute if you're going to utilize any sort of variable volume system. That way you never run the risk of that variable volume system turning down to be below that code required minimum of 500 feet per minute. So we know our CFMs, we have an idea of what our grease duct is going to look like, and what problems can we run into? There's really only a couple. Biggest one, you want to keep an eye for wherever there's swinging doorways, or wherever there's swinging doorways, or there's high traffic areas around the hood that could potentially either push or pull air into or out of the capture tank of the hood. The other one that's most easy to control, in my opinion, is the utilization of directional diffusers. So it's best practice to not have any directional diffusers within a kitchen space so that you're not accidentally throwing air back towards the hood and causing any turbulence under that hood. It's also best practice, or the rule of thumb that I always bring up, is not to have any diffuser within 10 feet of the hood. Now, I know that a lot of people hear that and they kind of laugh at me and they say, Mike, you've seen these kitchens that we're doing. I have to have diffusers within 10 feet of the hood. And I get that. There's ways that you just can't get around it. The best practice that I've thrown out around the country is not within 10 feet of a hood, and just keep them as far away as possible on those diffusers. The final issue or potential problem to mitigate is just insufficient makeup air. Now, in a lot of these engineered kitchen ventilation systems, we have some engineers that are expert in transfer air and HVAC and building pressure. So I don't see this one quite as often because that transfer air is accounted for. But if there isn't enough transfer air, if there's insufficient makeup air, you run the risk of starving that exhaust fan and not having capture happen. So those are really the only things to look out for is when it comes for potential problems in your kitchen ventilation system. Really, it's where are there cross drafts that are possibly running underneath this hood? A cross draft in a kitchen ventilation system will kill you. A couple other things that I'd like to point out. I mentioned to start that the overhang required per code is a minimum of 6 inches overhang from any exposed side to the hood. to the left or the right-hand side, you would need a 6-inch overhang from the edge of the appliance to the edge of the hood. That holds true for the front of the hood. So code is going to require a minimum overhang of 6 inches. However, I would recommend a best practice of, if you have some sort of a commercial oven, so a combi or a convection oven, that you have an overhang of 12 inches. Same goes for dish hoods, where these doors close, and then when they open, a bunch of condensate can run out. The reason being is that when you open these doors, so let's say you had baked potatoes in your oven for the last 45 minutes at 450 degrees. When you open that door, if the velocity of pulling that door, when that takes the air out of the oven with all that hot air, that velocity has the potential to supersede or over exceed that 6-inch overhang. So if you give it a 12-inch overhang at the front, it gives the hood more capture tank in order to overcome that velocity moving out. Final design consideration. Hey, Mike, I have the cross drafts here. I have diffusers here. This is a high traffic area. I can't move this doorway. What can I do? It's simple, but the best thing that you can do is you can apply end skirts to a hood. End skirts are going to come either be full end skirts or mini end skirts, or are your industry standards that you're going to see. And you've also started to see in the industry full insulated end skirts, but these are exactly what they sound like. They're metal, they're stainless steel skirts applied to the edge of the hood. And as you can see, they're going to potentially block any cross drafts that are present in your kitchen. Thing to note here from a design standpoint is that a mini end skirt, you still have to have 6 inches of overhang from the appliance. However, if you use a full end skirt, you don't have to have that 6-inch end overhang. You can go right up to the edge of that end skirt. The next question I always get from engineers on that is, oh, okay, then I'm just going to put a full end skirt on every single one of my projects. And that's great, because that would reduce the size, the length of your hood, because you wouldn't need 6 inches of overhang on each side, and it would improve your capture. The problem with that is that they can impede operations. So in my experience, cooks don't necessarily like end skirts, because if you think of this image, if you think of a cook on this image, and he's got a big pot on the back of this range. So he's got a big pot sitting on the back of this range, and it's boiling, he's making soup or something. When he goes, when he goes to grab that pot, he or she can't just swing to their left and put that pot down on a table sitting to the left, because there's an end skirt blocking it. So they got to take the pot off, take a couple steps back, move over, and then put it on that table. So they can impede operations. And if that's a concern, that's when you would use a mini end skirt, which will typically increase capture by about 10 to 20%, depending on the appliance lineup. All right, so the evolution of the kitchen design, and this is where I'm gonna kind of buzz through these first couple of slides and then we're gonna talk about makeup air in a little bit more detail. So the 70s, the 80s, the 90s, we had what was called short circuit hoods. These were, because that makeup air is so expensive to temper, they would utilize short circuit hoods, and they would bring untempered makeup air into the exhaust cavity of the hood, typically 90% of total exhausted air. The idea being that the air would be introduced right into the hood so it could be balanced and it would be exhausted right away. So we don't need to pay to temper it. But with the advent of CFD modeling and with Schleyer imaging, we discovered, or the industry discovered, that these hoods, the velocity of that supply air moving out of that hood is such that it's impeding the updraft velocity of the exhaust air, and it's actually causing heat rollout, and it's putting pressure on the HVA system as a whole. So IECC 2015 came out with this statement of replacement air introduced directly into the exhaust hood cavity shall not be greater than 10% of the hood exhaust airflow rate. Now, if you remember, that direct makeup air was 90% for balance. Well, now it can't be over 10%. So that essentially eliminates the short circuit hoods. So we're going to talk about the present now and kind of the future all in one. So designing of an exhaust system is going to be an exhaust hood with your exhaust fan. Best practice is going to be to have a 1-to-1 ratio of exhaust fan to exhaust collar wherever possible. Now, obviously, that's not going to always be possible just with the amount of roof penetrations and grease duct that you have, but that would be the best practice for design. And then you're going to have a dedicated makeup air unit. So this dedicated makeup air unit is going to be, it's going to supply air, again, typically 80% of total exhaust. It's going to supply that via an AST plenum. And then the rest of that transfer air is going to be made up with your rooftop air or any mechanical or gravity transfer, typically 20% transfer into a kitchen with the idea of keeping the kitchen slightly negative so you don't have smells escaping. Now, when you do these dedicated makeup air fans, you're typically going to have this image in the left. You're going to have what's called a perforated supply plenum, and everybody has a different monogram for it, but a perforated supply plenum. And what this is this is where you're going to bring in that heated makeup air. So let's say you made the decision to only, on your dedicated makeup air fan, only do heated makeup air. You're not even going to do cooling on that makeup air. You're just going to do heated makeup air. You're going to bring that air in. We're trying to pressurize this space, but that air is only heated. So in the summer or in those kind of transition months, the air is really coming in untempered. So you're going to bring it down right at the face of the hood. It's going to create what's called an air curtain. And now most of that air, I don't know the percentage, but a high percentage of that air is going to naturally shift back into the exhaust hood, and it's going to be exhausted right away. So that way we don't have to fully temper this air. So it's a better, not only upfront cost decision for the client, but also ongoing energy efficiency of not dehumidifying this air. I call it cutting the air, just bringing it down to within 10 degrees of ambient and then exhausting most of it. And then what does roll out the front of this curtain is going to be picked up by your rooftop units, keeping in mind that kitchens are energy hogs, and they're naturally humid. They are. Again, when I was a cook, it's not comfortable. All right. So the DOAS factor in kitchens. Is this the future? Does every kitchen need this? Do we just need to have DX cooling? Do we need to have cooling at all? Do we need to dehumidify this air? What do we need to do? That's probably the biggest and hardest question to answer across the country. And every pocket that you go into is going to do this differently. I can't tell you, hey, 50% of folks are doing it this way and 20% are this way. It really is dependent on the region and whatever the client's budget is or the owner's budget is for these particular projects that we're designing. So makeup air, so 508.1.1 is going to state that the temperature differential between makeup air and the conditioned air in the space shall not exceed 10 degrees Fahrenheit, except where the added heating and cooling load to the makeup air do not exceed the capacity of the HVAC system. What this has taken to mean across the country historically is that this gives a lot of deference to the engineer. So are we needing to just heat this air and then our rooftop units our HVAC system will be able to overcome the hot air and get that air cool? Are we okay with just having a hot kitchen in the summer and a cold kitchen in the winter? And the answer is, and I know when I was brought on today, it was, hey, what are you guys seeing in packaged DX cooling? I think up in you guys' area, it's just been summers are being hotter, so people are wanting cooling in the system. And if I'm being completely honest, there isn't a hard and fast rule across the country. Packaged DX cooling is absolutely used in a lot of kitchens across the country, and it accomplishes this exact same thing. It accomplishes this, getting the air to within 10 degrees of the conditioned space, but it doesn't dehumidify. And it has a large cost associated, versus just the standard heat-only makeup there. So what we're seeing across the country is small mom and pop shops, people that are just getting their restaurant open, whether that be here in Minnesota or in Wisconsin or I'm sure in Alaska. If people like that are just getting the place open, they're just doing heated makeup air. They're not doing any cooling. They're doing more middle of the road budgets or university style places or places with large HVAC systems are sticking with a kitchen with a more traditional kitchen application. So that traditional kitchen application is a kitchen makeup air unit with a primary function being to replace the exhausted air, and the secondary function being to temper that air within 10 degrees of the space temp, and then utilizing a rooftop unit with a primary function of controlling the space temperature. So that's the traditional, and I think what I have been seeing is that in smaller footprint, I'm jumping ahead of myself. So I said we're going to look at 3 different designs, and we are very quickly. First design is just a general store. Now, this original design was utilizing a DOAS unit still utilizing a makeup air unit with direct fired makeup air and cooling, and then a rooftop unit, which is fine. Nothing inherently wrong with this. It works. It replaces your outside air. It's slightly dehumidifying. But how else can we do this? And we can do it in two different ways. We could do it with the traditional kitchen design of that makeup air unit with a DX cooling and a rooftop unit, or we can do it with a DOAS system. So in that first example, that DOAS system was being underutilized for the tempering benefit since it was such a small percentage of the overall makeup air. So this design is going to drastically drop the price of the project, and it's going to save on roof space. So what I'm going to do is I'm going to increase the makeup air in my hoods by absorbing the DOAS's outside air. I'm going to add a standard RTU, and then I'm going to add diffusers for that RTU unit, and I'm going to bring my makeup air for my dedicated makeup air fan in through one of those ASP plenums that's going to almost immediately exhaust most of the air, but at least when that air gets in there, it's going to be tempered to that heating and cooling, but it's not going to be as expensive as that first option. Or we could fully utilize that DOAS's tempering and recirculating modes, and we could just eliminate the makeup air unit, thus saving us on roof space. So in order to accomplish this, we're going to move all of the air into the DOAS unit. We're going to eliminate the ASP plenums at the hood, because now that we're utilizing DOAS, you don't want to dehumidify that air and then immediately exhaust it. So you don't want to bring it in at those ASP plenums. So we're going to add diffusers to the space, and we're eliminating those supply hoods. So again, 3 different scenarios. I think it's pretty straightforward in my opinion. That first scenario, it did work, don't get me wrong, but that DOAS is so underutilized that it's just not the best way to go. The more traditional style is going with a dedicated makeup air fan and a rooftop unit. It's typically going to be your least expensive option, but you're going to give up dehumidification. And then the final option would be to eliminate the rooftop and the makeup air and then get full dehumidification out of the DOAS unit. So when's the right recipe for DOAS? What are we seeing out in the market? And really what it comes down to is these units are really nice for open concept for kitchens, small footprint buildings like a Speedway or a Holiday, a gas station store when you have just a small footprint, where comfort is key. So where we truly need to have that humidity control. And then so a place like a food hall. And what I would say is that, or what I've been seeing, and again, this is trying to look at everything from across the country and boil it down into where we're at, is that larger establishments that have more segmented, like here's my kitchen space, here's my dining space, whether that be a traditional restaurant or a hospital, in cooking, like here's my cooking space, here's my dining space. When you have those truly segmented realms, it seems to me that the industry is staying with a traditional makeup air fan and rooftop unit for that kitchen space. But when you have a more condensed building, a smaller footprint, more occupancy air mixed with the kitchen air, that's where we're starting to see the DOAS units. And it really comes down to understanding what that client is particularly looking for and what the budget is on these projects. So we got just a couple of more items here to touch on, and then I'll wrap up with a little doggy bag takeout menu for you, and then we'll open it up to anybody who has questions, and hopefully this is beneficial. So finally, grease extraction importance in kitchens. So grease is a huge fire hazard. Restaurant fires are common, and grease can be a serious problem. Increased operating costs by grease. You can see even when you have an up-blast exhaust fan on these things, I mean, you can get grease buildup on your deck line or on your roof line. And then grease, if you have poor filtration at the hood, that's going to lead to higher filtration, higher duct cleaning costs long term. So what do we do to combat this in the kitchen ventilation systems space? A couple of different things. So we are going to have grease extraction at the hood. That's our first line of defense for grease extraction. Traditionally, you would have a baffle filter. So a baffle filter, regardless of manufacturer, was never really intended to be grease extraction. It was actually intended to stop a rag from being sucked into the greasework, or if a fire did happen, or if an ember escaped, it was designed to knock that ember down so it didn't get into the grease duct and then start that grease duct on fire. Sorry, folks, I'm dealing with a little bit of a cold here, so bear with me. So the baffle filters was the traditional way, and really the only way that you could do grease filtration. Not very efficient. It's going to allow for a lot of grease to escape into the ductwork, and it's really not intended to do filtration. So what the industry has moved to, and depending on manufacturer, you're going to have either a centrifugal force type of a filter, which is going to spin that air and get the grease to drop out of there. These are typically anywhere from 60 to 70% efficient, 60 to 70 or 80% efficient. And that's just going to be a much higher filtration level with a slightly uptick in cost, but very low negative impact on your static pressure, so low negative impacts to horsepowers. The final grease filtration that you'll see this in the market, but it's very rarely used. And it would be some sort of dual stage filtration. These are going to be almost 100% efficient, but they're going to be extremely costly. And then they add a ton of static pressure to a system, which increases the size of your fans and costs associated with it. And everybody does these slightly differently, but it's these three stages of filtration are generally seen across the industry. And that middle stage, the centrifugal force, is definitely the most popular one that we are seeing, again, across all disciplines in the industry. Finally, pollution control units. So once you accomplish grease extraction, even if you have 70 to 80% grease extraction, even if you have extra grease extraction, there's still going to be grease escaping into that system. So there's three ways that pollution control units are operated, to my knowledge. I can speak to the two that I know the best, but there's also UV in the industry, which different manufacturers will utilize UV for pollution control units. But what I can speak to is either a filtered unit or an electrostatic precipitator unit. So what these are going to do is a filtered unit is going to be expanding stages of filtration from a 2-inch aluminum mesh all the way up to a top-of-the-line MERV filter, followed by carbon trays. Carbon is what's going to take the smell out, or an electrostatic precipitator unit, which again, depending on manufacturer, it's going to essentially come in two. It's going to be essentially three sections where there's going to be either a positive or a negative charged ion in that first section, then the opposite of that in the second section, so then it attracts to it, and then you're going to have your carbon filters to finish that out, and that removes the smell. The UL 8782 is the new standard in pollution control units. So what is UL 8782? It's a relatively new listing. And there we go. All right, so this is a kitchen-specific PCU listing where it's going. So previously, if you know, previously there was no UL testing standard for pollution control units. So you had to either use this weird combination of the UL 710 listing and of a grease duct listing, which this is a pollution control. It's not really any one of those two things. So there was no consistency in the industry on how these units were being tested. Now we have the UL 8782. So it's an actual UL certification for high temperature and smokes tests to ensure that the unit maintains proper structure under duress. And it's actually listed for pollution control units as opposed to that weird murky line of UL 710, ETL, UL 1978 for grease duct. This is a defined line. So where did this all come from? IMC 2021 requires any PCU to now be listed to UL 8782. IMC 2018 required that PCUs be listed to 1978, which was a grease duct standard. And then 2015 didn't mention PCUs at all. So it's important to note that PCUs now from IMC 2021 forward are into the UL 8782 listing. So thank you all for listening to me today. Some of the key takeaways are if we keep up with the what's cooking or what's on the menu, what's our takeaway, what's our to-go order? KBS design belongs on the mechanical side. We can have conversations on this, but ultimately the mechanical engineer in almost all instances is the one trained in that discipline for HVAC. And this is a system. So regardless of what side it lands in, these KBS should operate as a system. Utilize demand control ventilation whenever possible. The price point between the constant volume and the variable volume cost, again, across the board, has come much closer, and the overall payback is extremely good across the board. And it's just a better energy consumption item. So DOAS, heated makeup air, cooling makeup air, whatever the case may be, apply it when necessary. So there isn't a one-size-fits-all application for, do I need to use cooling? Do I need to dehumidify? Do I need to have cooling at all? Should I have packaged or split? The conversation is really to be had with looking at what the application is, looking at what else is going on in the HVAC system, and then understanding what the needs and the wants of the client are. I think the reality that I've at least seen in my experience is that when I start working with an owner or an ownership group on a project, we want to have the biggest and the best and the brightest. And then that price tag comes in and it's, okay, where can we value engineer this? So there's no right answer to DOAS, to cooling, to not cooling. It really comes down to the engineer and the client having a conversation about the positives and the negatives. And then finally, grease, odor, smoke removal. Again, I would move away from baffle filters. They just were never intended for filtration. I would move to some level of a centrifugal force filtration at the hood. And then knowing that pollution control units are now listed to that UL 8782 standard, which is an actual pollution control standard. And then the other thing is PCUs are just becoming more prevalent in the industry. I am not going to pretend to be an expert on what we're seeing in Alaska. But I can tell you, I was in Chicago, Illinois last week. They're looking at mandating them. New York, obviously, Minneapolis, Minnesota, where we are here, Woodbury, Minnesota, most of California. So they're coming in the industry. It's just a matter of where it is along the way. So it's good for you guys to understand and know that there's now a true listing for them. So there's a strenuous test that these all go through. All that said, I hope that this I know it's high level. There's only so much that we can, I could talk about kitchen ventilation systems for 9 hours and the different pieces to it. I'm happy to have some open conversation with folks. But from there, I would open it up and say thank you for your time. And again, hopefully you found this information beneficial.
Thank you, Mike. I just have one question on the chat box. It's from Jenny. She says that one area that we have a problem with in the local design is people designing the hood with the supply air plenum and then dumping 90% of the required makeup air in the plenum and short-circuiting the hood. It's a big problem here.
Yeah, that's a big problem everywhere. That's why this stuff needs to be in you guys' scope. So if I could repeat that. So it sounds like we're using a ASP style plenum, and you're putting 90% of supply air right into that plenum, and then you're having hot spots coming down. And what I would say to that is rule of thumb is 80%. I can't control what other people do, but rule of thumb is 80%. And then if you have to go 90 or 85 or something like that, when you're actually designing the plenum, so the plenum itself will have supply collars along it. And what I shoot for is a velocity coming out of that collar of no more than 500 feet per minute. And that will typically eliminate some of those hot spots. And that allows for the air to expand further along that plenum. And then you don't get that short circuit effect. But yeah, there's no way around it. If someone's going to try to put 90 or 95% makeup air through those plenums and they have tight collars, you're going to have problems.
Okay.
But again, 80% would be our recommendation.
Okay. If anyone else has any questions, please type in the chat box.
Well, hopefully that means I answered every single one of these, and you guys are now perfectly experts. But know that this is always updating, and there's challenges across the country. So, yeah, again, hopefully you guys hopefully this was good.
That was great. Thanks, Mike. I haven't seen anything pop up in the chat box. Appreciate your time. Thank you.
Yep. Cool. Well, I'm going to run that, and you all have a great day. Thanks again for your time. Bye.
Yep.